when is the next training? Is there one today? Training, clean room training, safety training. It was? It is? It was. Okay, and the next one is? There's one more, or this one? This is the last one. So, who qualified in the previous one? Okay, so we have, who took it today? Just one. So it seems we are in good shape. I'll have hopefully good news for everyone today from Nadir. He lets me know pretty soon. Alright, so we were looking at some basics. Don't worry about this. I don't think so we'll get to this guy before next week, because today we'll look at semiconductor materials, some overview of all the different modules that we'll be looking at. And next lecture I was planning to talk about clean room. Clean room, what is clean, what do we mean by clean? Because the week after is when we are planning to get into the clean room. I hope you guys have your notebooks by now.
I've ordered them, they should be here by next week.
So you will be next week.
By next
Tuesday
Monday.
we go in the lab.
Monday
Wednesday.
we'll
Okay. So, yes ma'am.
What's the difference between clean room notebook and the lab notebook?
The paper that goes inside the clean room is different than regular
Yeah, I
paper.
know. A lab notebook and clean
Stays
room.
outside. So clean room notebook is where you take your data. It's mostly just a compilation of things that you observe. And your lab notebook is where you write the actual observation, and it's more neat and more ordered. I'm not saying your clean room notebook should be disordered, but lab notebook is what stays outside of the clean room.
So when you go shopping, you need to order.
You'll have to maintain both of that, but you'll be graded only of the lab notebook, which will stay outside of the room. Right? Because that's something which you can take home and work on.
Particular size.
For the lab notebook, no, it's a standard page. So it's
Can you
just
use the regular notebook for the lab notebook?
as long as it has page numbers, that's fine. It has to have not handwritten, but the printed page numbers. That should do it. So I hope once we start the labs to even out the numbers of students. So as the makeup right now, we have 9 students in one section and 3 in the other one. So I'll be requesting, or if you want to volunteer, works for me to put 3 of the students from Wednesday lab to Friday. So we have 6 plus 6. So if you have, anybody has preference, talk to me. If not, then I'll have to take the last, those 3 who registered last, or we'll find out but some mechanism, but we'll want to have equal numbers of students in both of the sections. So we have labs on Wednesdays and Fridays. So I need 3 from Wednesday to go to Friday. If you want to do it, volunteer yourself, talk to me. If not, we'll have to do something about it. So we'll talk about this later on. So this is more on, today's lecture is more on fundamentals. So something what we have seen in high school chemistry, right? So there are, we know the periodic table. So fourth group is where we have carbon, silicon, germanium, and the distinguishing factor for this group is that the outermost electron shell is completely filled, empty, half filled, right? So the outermost shell is, say it again, you said it all, is half filled. What does that translate to? That neither it's conductive nor insulated. So it's somewhere in between, as long as we can push some electrons in or take some electrons out. we can change it. So that's the quality of semiconductors. So we can, and these are group 4 and what are called elemental semiconductors. Now if we make a compound of 3 and 5, so 3 would have how many electrons in the outer orbit? 3 and 5 would have 5. We bring them together, they share, and the end result is we get outer band to be again half filled. So we can use them as compounds, so we call them compound semiconductors. We can use compounds of 3 elements as well. So in that case, it's called ternary compound. Again, it has to have the same property that outer orbit has, is half filled. So there, and that defines their conductivity, which is somewhere in between in metals and insulators. Thinking about a simple diode. And I hope all of us are familiar with diode. What is a diode?
Something that lets current flow only one way.
Something that lets
It's a circuit element that lets current flow.
Okay, yes, you're right. But more specifically, a diode is 2 types of material, which may be same element, but their type is, when we say N type or P type, they are in intimate contact with each other, right? So they are bound to each other. Or maybe that was a one bulk, but we doped one part to be P type, the other one to be N type, right? So that, what's the function of diode which you were telling?
It lets current
flow in
one way or
one
the other.
way and doesn't in the other way. So that's the function. That's not what is diode. And which direction it lets it flow? If we do, what kind of biasing allows forward bias? And forward is what? P2 and okay. Well, how do we define forward bias? So it's supposed to be how we bias the diode. So it's supposed to be the voltage source. What is forward bias?
Minimum voltage required to bias.
Positive terminal goes to P type, negative goes to N type. So essentially, we can change the properties of semiconductor material, and we can use it in different configuration and achieve some electrical function out of it. Right? In this case, the function is called rectification. Right? Rectification, where the current will pass in one direction, not the other direction. And what is the rectifier? AC to DC. So it does some operation, which is conversion of alternating current to direct current. So all goes down to, what we are concerned is, it all goes down to semiconductor material which has been given different electrical properties. And 2 parts are given different electrical properties, they result into this function, what we call rectification. So all steps. Always I would want you to, or we would like to develop this thing in this course, that you look at the fundamental material. Because if you are the one who's fabricating device, so yes, you have to know high level, it's a rectifier, but you have to know the low level and material level, what kind of properties you are going to give to the material, to that wafer, right? So you have to know that. So this is more fundamental. So we have silicon, germanium, those compounds are aluminum, phosphate, and so the ternary compounds, where we have different fraction of elements that come together. Now, gallium arsenide has good optical properties, but something which we know now, that why we use silicon, why silicon has become backbone of the whole semiconductor industry.
It oxidizes in the oxide insulator.
The ease of growing oxide and the electrical properties of oxide are very different. If it was germanium, if germanium could have done the same, we might have had germanium. So
why is germanium so great?
Why is germanium so great?
Or gallium arsenide? I mean,
they have different property. So, okay, that goes down to device physics, where for different applications you want different device parameters. So, the material, we probably will look at that in terms of mobilities and all that, but yes, they were not used because it was hard to get an insulating material grown out of them. So I had the answer right there. So friction of elemental component. So we'll get into that also, where we can change the band gap. Band gap is something where we have a valence band and a conduction band. Again, basic chemistry. We have to have, for conductivity, for charge transport, we have to have an electron jump to conduction band. So we can change that by changing the friction. So you'll see ternary compounds most of the times written as this subscript. So that will tell you maybe aluminum 0.3, gallium 0.7, and arsenic. So that will tell you. So that changes the electrical properties of that material. So these are major uses of silicon dioxide. Two most important use: gate, which is, I drew that transistor last time. So there was this part where you had to have an insulator layer, and you apply some voltage on top of that, which results into accumulation of charges, which connect source and drain. So there is a path of travel. That is where we want to use oxide called gate oxide. And in other words, field oxide, where we want to isolate electrically active devices from each other. Right. So, okay, simple crystal sodium chloride, right? We use that, but why? So this is simple idea that there is a repetition of atoms. There's repetition that the structure has a long-term order to it, right? So long-range order is the keyword. Sodium chloride crystals are not long-range. So you have small grains. So there is a structure, but it is confined to very small area. What we want is, in a semiconductor, that they have long-range order, what we call single crystalline structure. So there's no break in that structure. We call it a single crystalline structure. It's also called lattice.
So that means are metals crystals?
Are metals crystals? So first we have to think, what is the orientation of each atom in a metal? Is it exactly bound to same number, or the placement is periodic of atoms in that structure?
I'm not sure.
So that's, if you look at that, that answers are they are not. So there is no long-range order in metals.
See.
Right? And we'll see why, when we deposit metal or we etch metal, how does it grow? How do we make thin films, or how do we get physical deposition of metal? So that's an entirely different process. Just because there is no long-range order. What do we call a material that does not have long-range order?
Amorphous.
Amorphous materials. Amorphous. Now think about it. Carbon. We, I think, looked at this example. So amine is composed of carbon. Charcoal is composed of carbon, right? So those, what we call graphite pencil, they also have carbon. What distinguishes three carbon materials is the long-range order. So graphite does have crystalline structure, but it is not long-range, right? But charcoal is completely amorphous, so there is no order to the atoms in that structure. So think about it. If something has very precise, dense, if something has very precise order, it will be dense as well because there won't be any free spaces in between. But if something does not have that kind of order, there will be free spaces in between. So density would be less. And this is exactly what changes the electrical and physical properties of the material. We use diamond to cut very hard materials because it is so strong. Can you imagine doing that with coal? Because it's not compact, coal itself is very fragile, that matter. So in a two-dimensional structure, this is how we have been trained to think about crystals, right? Sodium chloride, so we used to, what was that? Force model, all those things that they taught in high school chemistry. Like every third lecture was something that refuted what we learned 2 weeks ago. Remember that? In high school chemistry, they were explaining to us structures, and after third lecture, they would say, okay, that theory was wrong, but we taught in the class. But ultimately, we have this a two-dimensional picture in our mind, where we have nucleus and we have electrons going around it, circle around it, right? Essentially, it's not two-dimensional, it's a three-dimensional structure, right? So where we have what you call the different bands, and they have different sizes. So when you say long-range order, they come in a three-dimensional system like this, where the whole cell, now this is called unit cell, can be as simple as like this, where you have just 4 atoms, can be as, I don't know, complex like this. So it's a whole different branch of science, what we call crystallography. Right? You will just skim the surface of it without going into too much detail. There are other courses where they talk about crystalline structures. But here we'll just constrain ourselves that this is called a unit cell, and each cell has different number of atoms. Each surface of that cell has different number of atoms. If you stay with me and look at this top surface, how many atoms do we have in the top surface? So it's a cube, right? So look at the top surface of the cube. How many atoms do we have in the top surface?
Apparently 5.
5? Anybody else?
Which surface are you?
Top surface. So if it's a cube, there should be a front, a back, top, bottom, right and left. I'm talking about top. How many are there? 5? 5. It's 5, as I'm showing you. It will get more complex. And now think about it, if I call these edges as A, B, C, D. Now think about a plane composed of A, B, C, D. How many atoms are there? Not 5 for sure, right? So it's hard to imagine how many fall in that plane. But there is a plane. There can be a plane, right? There can be a plane composed of, what do you call it? Similarly, so can be A, B, C, D, or if I, so that's that. So I can define a plane which is composed of A, C, D as well, right? Which will be a triangular plane. So each will have different number of atoms. How do we, why does it matter? If there are different number of atoms in different planes, why would it matter? Density of atoms will change in that way. So if my wafer, on which I'm going to make my devices, has top plane on the top of the wafer, it will have different density of atoms. If my wafer that I'm going to use for device fabrication the top plane is ABCD, it's going to have different density of atoms. Right? You guys are with me till here? Now if I have different density of atoms and I react it with something, do you think the reaction that happens on A, B, E, F is going to be the same as reaction of plane A, B, C, D? Reaction. What do we need for a reaction? We need two atoms, right? Or molecules come together. But the different density of those atoms. So reaction is going to be different. So process, whatever process we do on a wafer, have different parameters, different outcome for different planes. Do you agree till here? So that's why we need to know a little about planes. So something which is, there is a periodic arrangement called lattice. It shows long range order. Amorphous are that show no order. Polycrystallines are which show order in small regions. And then there is amorphous region, and then there is some, and then it goes on like that. Again, a little more stressful example of that. There, yeah. Now this is example of a crystalline material, an amorphous material, and a polycrystalline material. You'll have some order, but then there is boundary of grain. So this is more like a sodium chloride type of material, right, which doesn't have long range order in it. So silicon has what we call diamond cubic lattice, where atoms are tetrahedrally bonded by sharing valence electrons. So this is an example where we have the height, the basic measurement of units of 5.43 angstrom and inter-atomic distance. So again, different planes have different number of atoms. But we see something that the top plane and the bottom plane have same configuration. So they are called equivalent planes. Right? Similarly, if I have sort of that what we call ABCD, this plane. So this plane will be repeated in next cell, right? So all those planes will be called, they'll be called what? Equivalent. They are equivalent. They are same. They appear at different depths, but they are essentially equivalent. So if I know one, I know all of the rest. How do we identify these planes? It's something called Miller indices. So we define Miller indices. So Miller was probably the name of the gentleman who came with this framework of classifying crystals. So what we do is we take a unit cell and we align it to axis. So we say on each side the length is A. Right? There are some things which we know that parallel planes will never cross each other. Right? Parallel planes which are perpendicular, they would cross only at one line. Right? So we know all those basic axioms. So if a plane is cutting Z, it will never cross X and Y. Right? Make sense? Ninth grade geometry, because I'm teaching this to my daughter nowadays. So we know these basic things. So these planes have certain properties to that. So how do we define that plane? We define it how it intersects the main axis of the crystal. And we defined set of integers called HKL. Okay, it's written there, Miller indices. So HKL is what we define. So we say, okay, this is A times A times A, right? I color them. I say, okay, blue plane intercepts it at A00, red plane intercepts at 0A0, and yellow plane intercepts axis at 0,0A. You agree? Right? So this is Y and Z is 0 here. So the only thing what we
So
have
is
A.
Electric, well, I've been confused about this for a while. Is A an integer or is this,
It's an integer. It's distance. It's an angstroms for unit cell.
Oh,
I
really?
just showed you that number. What was
So,
it?
there's
5.24 angstrom was for.
So we call them 100, 200, 210.
So what that defines is, we generalize the indices to know what plane is available on the top, without going into how deep is the unit cell, because that is something which is constant for silicon, for example. But the plane that is available may be different.
I see.
Let me
So
see.
the different extents of the crystal may be different, right? They need not be cubes.
Unit cell dimensions will always be the same, right?
I see.
It's the how that unit cell appears at the top surface. That's what will define if it's 111, 100, or 101, whatever plane is available on the top.
I see. So
Do you understand his question? So he says, he's leading us to something which is going to come on next slide. So it says essentially how we define a plane is by digits: 100, 112, 001. So 100 basically means that we have a plane which is x, y, z. 100, 1. So it's cutting x-axis at 1. So we have the plane available on the top, which is equivalent plane of a plane which would intersect x-axis. Right? And then we would know what is the configuration of a unit cell. That will tell me how many atoms are there in that plane. So Miller indices don't tell me essentially how many atoms are there. It just tells me what plane is at the top. Just bear with me here. So this cube is composed, it has billions of cubes next to it, right? So suppose the crystal is laid down in a way that the red part is facing to the top. And what is the vector of a surface? What is the direction of the vector of a surface?
you mean it's normal?
It's normal, always, right? What is the direction of a vector of a surface? Yes, you know that. It's always normal, right? It's always normal. So once I define this red to be what is available on the top of my wafer, I know this is 100, and it's always taken 100 like this. So I'm going to define a vector coming out of origin going in this direction, basically equivalent of this plane. But let's look at how we calculate these.
So are you saying the yellow is the z plane, the y is the red is the y plane, and the blue is the x plane? Is that?
Oh, yeah. So what is the direction? Again, what's the direction of the vector of the surface? Right.
Okay, I see.
So follow the process. How do we get to Miller indices? And that has all these underlying principles which we know for a long time, haven't polished that yet. So So what are the intercepts for x, y, z? So we find the intercept for the three planes. So blue is A, there's no intercept for y and z. So those are infinite, right? So flip them. So 1 over A, so A over A, infinite. So divide them with the unit cell length. So we get something and then flip it. We get 1, 0, 0, 0, 1, 0, yeah, and 0, 0, 1. Does it make sense? How do we get to those numbers? So now, when I say I have a 100 crystal, what would that mean? So it's essentially a plane which is the front of the cube, right?
Oh.
And the back is
So-
equivalent to the back plane.
Yeah.
It's equivalent plane. So if I have a plane where I say it's 0, 1, 0, what would that be? It's a plane which is red, which is parallel to y and x, and it's in the direction of z. Now, I know this. Now I will go. I'll look up. Okay, what is the material and what is the unit? How does units I look like of that material? Does it make sense?
So
And that will tell me how many atoms should be there in red plane and blue plane or yellow plane. Right?
So, Dr. Was this as simple as saying the 100010001 are the vectors defining normal the surface planes?
Yeah. And we call plane. So what plane is this wafer? You'll tell me it's 100. That's all I need to know.
So it's the x plane. So how about 110?
We'll get to that very soon. Let me make sure this sinks in what we have right now. Right? So 10010. Now he's just trying to confuse us. What about a plane which is a triangle between three corners? So it can be a plane like this. Can be a plane like this, right? And all the other configurations. How do we define them? This is how we define them, right? So if you follow the process, you will always get these. So that will be 110, 111, 200, 100, 01. So essentially, all other planes are equivalent of these planes. Does it make sense? All other planes are equivalent of these planes.
I get everything except 200. How is it 2? Is it 0.5 inverted?
Yeah. So we flip those numbers.
Oh, the
Remember?
zeros are infinity
Yeah.
inverted.
So you have the unit cell. So you have to divide it with unit cell and then you flip it. That gives you
Okay.
2. Right? Make sense? Why it is important? Again, so whatever plane is available on that wafer will define properties of that because of that wafer. Properties of etching, properties of oxide growth, because there will be different atoms available in that. So now we can do a little more rigorous discussion that if I have these 4 atoms on 4 corners, so now, okay, now these are the vectors that define those planes. Right? So I know the plane, now vector is essentially normal to it. So this vector is 100. Right? We just saw that the front was 100 plane. So the vector is 100. So we call that vector the same as we call the plane. Make sense? And they are equivalent. So one that is behind is equivalent to this guy. Now if I say, okay, if I have 4 atoms in this plane, how many atoms do I have in this plane? 3, right? How many atoms do I have in this plane? 4. I have 4 atoms in this plane as well. But what's the difference? More dense, right? So density is different. So it's not just how many atoms are there, it's density as well. And this is simple unit cell. I showed you there. What we get, especially for alloys, primary alloys, a much more complex unit cell. Where you have atoms at different angles bound to each other. We will not get into that. We'll stick to silicon now. Right? So now this defines by wafer, of course, size and orientation of it. So if I have a wafer which is N-type and it is 100, it will have two flags. One primary flag, also a major flag, the other secondary flag, smaller flag. Flat is nothing but side of wafer is ground, right? Made plane. So everything else is perfectly circular. We put this. So these are for 4-inch wafer. So this, okay, and this is now 16. We are making 16-inch wafers now. How do we make crystalline silicon? By pulling out ingots of silicon from molten silicon. Right. So the ingot is pulled out from a what we use as a what we call that thing which is crystalline.
Seed.
We dip it, seed, right? So we dip in the seed in molten silicon, and what do we do with the seed?
Pull out.
Pull it out. So if I pull it too fast, what's going to happen to the ingot? Versus I pull out.
It'll break,
slowly.
or it will be too
Okay,
thin.
suppose nothing breaks.
It'll be too
Diameter,
thin.
yes.
So diameter will be different. Diameter of ingot will be different. So, right? So that will define how big final wafer is. If you look at the ingot, it's as rough at the edges, right? It's rough from the outside. So this is polished very well. You get a perfectly circular shape.
Now,
And then
what-
this is chopped.
How do you get a circle? Shouldn't you get some sort of square or rectangular prism with the crystal structure as given?
Yeah, it should be, but what is the question that comes to our mind is why portholes are circular? You know what is porthole?
Oh, I see. Because you cut them with a.
Is it? Doesn't belong to silicon. It has nothing to do with silicon fabrication, but question. Have you guys seen, do you know what is porthole? What is a
To
porthole?
hold the ship that you can.
Follow the ship, right? We are listening, hearing about that ship in Italy. The porthole is that opening in the wall, right? And they are made circular. Have you ever seen a square porthole? Why do we make circular portholes?
Easier better structural stability for the rest of the ship.
Yeah, so the energy is minimized on that circular shape. So in this case, we call it free energy or call it entropy. So things like to be in circular shape to have minimum surface energy. That may be the reason. I don't know exactly why, but
But we don't cut it to a circular thing. It's not
this
like
is
a
how
circular
this
ball.
is exactly how it comes out.
That's interesting.
Right. So circular shapes are minimum surface energy. Means they don't have too much inherent energy to them. Right. So there are two ways how do we make crystalline silicon. One is called Churalski method. The other is Bridgeman or moving. We'll see what is that called. I'm forgetting the name. But remember the flats. So once you are given a wafer, you need to know there's no information in the wafer. It's just a disk, shiny disk, nothing written on that. You should know how to know what kind of doping is there in that wafer. What's the orientation of that wafer? From flats. It will always have a flat. Right? And more often what we do is we hold that wafer from that flat. So we use tweezers, we hold that wafer from that flat region. Alright, so they come in all sizes. We use alternatively, we call it 4-inch, 100 millimeter, and so on. So 16-inch and 400 millimeter wafer. So both terminologies are used for that. And essentially at the end, we cut out the die from that. Right? So how do we make semiconductors electrically active? We introduce some impurities called the extrinsic semiconductors. What does that do? It causes charge carriers and changes the conductivity of the material. Now this is something which we should have back of our mind. If I put a lot of dopants, should the material become highly conductive? Do you think it should be a linear relationship with them? Right? So if I dope something to maybe 10 raised to power 60 and I dope another substrate with 10 raised to power 19, these numbers will become easy for you once you know what does it. If I dope it even further, the conductivity should become better for the substrate, for the wafer, right? Wrong. Because what we are thinking when we say this, we are thinking in terms of metals which don't have any order. But in crystals, we have a long-range order. We have a structure of rigidly bound atoms, right? And we are introducing impurities, atoms of something else, which go and kick off those silicons and take their place, and they contribute their electrons, or sink some electrons, so there are holes which are contributed. There is a different concept for semiconductor materials called mobility. So mobility is important and not the conductivity. Conductivity is more relevant for metals, where we have this sort of a notion that Ohm's law, the more voltage we apply, the more current will flow. There's no similar thing for doping versus semiconductors. If we dope them too high, mobility goes down because of collisions with the lattice, the collisions with the static atoms. So make sense? Those atoms are rigidly stable in their position. It's just their holes or electrons that are traveling. So we have a very well-defined structure which results into degradation of the movement of charge because of collision. Right? So mobility. So yes, we dope them, but there's something called mobility which falls off if we dope them too high. Right? So we look at mobility also, but generally we dope them with two types of materials. One is N-type and one is P-type. And we know that N-type contributes electrons, P-type contributes holes. Right? Knowing the actual physics, there is no contribution, there's nothing like holes, it's just the vacancy of charge, what we call holes, but we treat it as a charge carrier. Right? So
when we speak of current flow, we speak of hole flow, right? Not electron flow.
charge flow. You will seldom hear me saying current flow. Charge travels. Right? So hole, we treat it as positive charge carrier. So in device physics, it's treated as an entity that has mass, charge, all the same properties like an electron. Right? So it has to have valence greater than 4, so it can contribute 1, and the extra one, they can be easily excited to travel. And P-type is that has less than 4, so yeah, so it produces holes that travel. So it sinks electrons essentially. So P, phosphorus, antimony, and arsenic are group 5 elements. 5, they have an extra electron used for N-type grouping. So when it says requires less energy to excite it to the conduction band, it's in comparison to P-type materials where the holes are considered more bulky and they requires more energy, bulky in terms of their mass. So P-type dopants are boron, aluminum, gallium, indium, and less energies into the hole than into the conduction band. So excite the electron into the hole than into the conduction band. Essentially, bringing it back to valence band is easy than to kick it to conduction band. So we need more energy to create holes in the material. So group 3 are acceptors, group 5 are donors. And again, in terms of electrons. So they accept electrons, they group 5 donate electrons. This is repetition of course. So the crystalline structure of silicon defines its physical and electrical properties, and it is, if we have single crystalline silicon, the effect of doping is different than if you do that with polycrystalline silicon. What is polycrystalline silicon?
Silicon with small crystalline regions.
There are small regions of crystalline structure, so we don't have long range order.
Why do we need to dope polycrystalline? Are they more conductive as
Polycrystalline silicon, or what we call polysilicon, is semiconductor. It doesn't have long range order, it has grain boundaries. So we have essentially some region which has crystalline structure, and then there is a break in structure, and now you have another crystalline part. So that break is called grain boundary. So you have, now think about it, would just looking at semiconductor without doping, which one would have more resistance to the flow charge if there was some charge? What is
The polycrystalline.
polycrystalline? Why?
The grain boundary.
There is an extra impediment. There is an extra resistance, which is the grain boundary. Make sense?
Why would you ever want to use polycrystalline silicon? It seems unwieldy.
Yeah. So it's a very fundamental, very important question. Polysilicon can be heavily doped. It acts almost like metals. Okay. Why don't I use metal directly, and why am I worrying and using polysilicon? Because polysilicon has almost same thermal behavior as silicon. It's different, but it can withstand high temperature. A metal cannot. So if I need to do some thermal process after I put conductive material, I cannot use metal there. Are you following me?
So you could actually make lines
With polysilicon,
with
heavily
polysilicon.
doped polysilicon, and they will act like conductors. And now I can do heavy thermal
You
process.
could put them in your 800-degree furnace. And
800, 1000, 1100, whatever. It will get oxidized, right? But not at the same rate as single crystalline silicon, because single crystalline silicon has certain density of atoms available for oxidation, reaction with oxygen, single crystalline, and polysilicon has entirely different.
do we have wafers of it, or is this something we use for
We deposit
deposition?
it.
I see.
Deposit
I
polysilicon.
see.
We always deposit. They come deposited as well. So, but essentially, we don't get the wafer made of polysilicon. We always put on.
So can the structure of the grain boundaries be controlled? Or
We do control them. Yes, sir. Yeah. So that's a very interesting thing when we get to deposition. How do we control the properties of film? Well, we can deposit gold by different processing, but they'll have different properties. We'll see why. So gold is just an example. Anything that's deposited, we can control many things. Right? So, yeah, so crystalline silicon is what is essentially a semiconductor. So polycrystalline is where we don't have long range order, and we can use it heavily doped poly as conductor. It is used as conductor essentially. Right, so why silicon again? There are a number of things apart from the good oxide. It has many uses. It has abundant, easy to purify, good crystal quality, strong and hard material. Doping can be controlled. Physically, it has a band gap which is easily used in electronic devices. What is band gap?
Distance between the valence and the conjunction.
Distance between valence and conduction band. Okay. Why is it important? Do we want a large band gap or a smaller band gap? The engineers, okay, think about application. Do I need my classroom on 6th floor or do I want it on 1st floor? First floor, too much noise. You see kids sitting in the atrium, so much noise. Do you want it 6th floor? So too close to Dean's office. Band too small of a band gap would mean that it will be very easy for electrons to jump into conduction band, almost band, right? That kills my semiconducting behavior. So it depends on application essentially. But too big of a band gap, I will have to pump lots of bias. I will have to pump lots of potential to make electrons jump to the conduction band. So activation of device will require certain heavier biasing, right? So more biasing means I have to pump more energy into circuit, which means more dissipation and more power consumption. 1.1 electron volt is something that requires how much voltage for diode to start conducting? 0.7 volt, right? Which is very almost it's become a standard, right? So we design everything around 0.7 volt, which is even something that we can achieve with the battery, right? 1.5 volt battery can achieve that. So band gap directly translates into how much power we need to do. And do we get control over conductivity or not? So high breakdown voltage, so it takes certain voltage before we can bring it to conduct. No deep traps, indirect high carrier lifetime. We'll look at carrier lifetime later on. And mobility for both is reasonable. We'll look at mobility also, why it is, which value is important. But essentially, silicon was used for the oxide, and everything has been good about it. Right? So it's grown in ingots, sawn into thin wafers and polished. So for silicon, what the planes which we get are 100, 110 and 111. We get many more planes for other semiconductor materials, but for silicon, we get these 3 planes. So this would essentially tell me a lot about the simple processing I want to do. And we'll see, we have a lot of characterization for different processes. So for 111, I can easily pull off that information for any process. For oxidation, I would know at what temperature 111 will behave in what manner if I'm doing oxidation. So compared to 100. So we need to know these planes. So yeah, this is called Choralski method. So what do? We melt down silicon above 1421, insert the seed with precise orientation. We grow a thin neck, and we pull it out. And our pull rate defines the size of the ingot. And once we get it out, we break the neck, and we have the ingot for sawing and use. What we can do is we can impart impurities while we are doing that. Hardly we ever find silicon which is not already doped. There's certain doping that is done during the wafer production. So that is is very critical. How do we control that? So there is something called equilibrium segregation coefficient. So these numbers define that what kind of impurity we can incorporate. So smaller the number, the easier it is, right? So the equipment consists of furnace, mechanism to pull it out, ambient control, and the control on the how fast you want to pull it out. So these are different parts, but the essential requirement is we don't want any unintentional impurity into the melt. So we have inert gases and we use quartz crucible. In this in situ metrology to control the process. So in situ is a process, something that can measure the outcome of process while it's happening. What might happen if you have unintentional impurities into silicon? What would happen if we have unintentional impurities into silicon?
Well, it would have different conductivity properties than the ones you desire.
So we will not know the electrical properties, electronic properties. We wouldn't know if it makes it metallic. It incorporates metallic atoms. Then we have no gating effect. We can't control the band gap if you get those impurities in them. Another process, it's called float zone. So float zone is where we have a polysilicon rod, and what we do is we have these coils which melt the rod as they travel along the rod. So once it melts in that localized place, once it solidifies, it follows the crystalline structure of what's coming below. So we have the seed for this guy as well. Once we start moving the float zone is it's simply a zone where we have molten the silicon. And once we move it to the top, the lower part follows the orientation of this seed. Right? So what results into a crystalline silicon. Again, you can slice it and get the wafers out. So this is essentially the process where we have pulled crystal, we dice it, we saw it, we grind the edge, we flatten the wafer, etch it to the desired thickness, polish it, and comes out for the user, the rest of the world. So essentially the size that we get after sawing is thicker, but once we get to here, we bring them to the desired thickness that we want, and then we polish both sides or one side. Generally, what you guys will be using will be single side polished wafer. So it will be rough for one side and polished from the other side. Guess which side will we use to make devices?
Polished side.
The polished side. Right? We do use both side polished as well, but that is a technology which is used in industry. So industry uses both sides of the wafer. They don't want to miss any semiconductor material to make devices. So they are double side polished. And there is a special type of those wafers. We'll look at those. They are called SOI, because silicon and insulate wafers, which are double side polished. So how do we define the a wafer? So we know a few things now. We need to know crystal orientation, right? We need to know size of the wafer. We need to know what is the doping in the wafer. Is it N type or is it P type? Right? And a bunch of other things. The thickness variation, how big is the flat, what's the orientation. So all these things we need to know before we start our devices, right? And again, guess what? Do we want our wafer to be warped, or do we want it to be perfectly flat?
Perfectly flat.
Flat, right?
Simple reason, we do many things where we put it, we might have it standing to do processing, but a lot of times we want to hold a wafer down on a vacuum chuck. So chuck is a round platform that has grooves in it, and we apply vacuum through those grooves. Once you put the wafer on top of that chuck, the vacuum sucks the wafer down. So it's very hard to move that wafer. Why do you want to do that? You rotate it on thousands of RPMs to do some processing. You'll see what is that. So it has to be very flat. And the mechanical properties, we don't want notches, we want to have perfectly round contours. Chemically, we don't want defects. We want it to be single crystalline silicon. And surface has to be flat and clean, no particles, very clean. So once you get a wafer, of course you will be covered to save your wafer from you and to save you from your wafer. So you'll see it is very plain, very shiny thing. And essentially we do dirty processing on top of that, but after every process we clean our wafer. So we bring it back to that very mirror and shiny condition. Yes, ma'am.
I'm confused about one thing. The flat side that we said for a P-type or an N-type, that is done at the time of growth or after it is done?
After the growth, once they chop it, then we put the flats on that wafer.
So flats are done after diffusion takes place.
Diffusion?
For N-type and P-type, it means
No,
separate.
we haven't talked about diffusion yet. Those impurities are mixed in that molten silicon.
Oh, so they are not, okay.
Be very careful. Diffusion is the process.
Okay, so that's,
So that impurity is added in that molten silicon. Fusion is something what we do ourselves, when we dope it, heavily dope it to our taste requirement. Taste. So as the size has been going up, we can have much more chips, much more dies made in one go. So that brings the cost per die down. So it is called economies of scale. So this is something that shows it's still old data, but its cost per transistor, which has been coming down. So scaling has been going up. So our yield is becoming smaller, but our annual the percentage is almost the same in cost per. But what we see that there are many more chips that we can make on, and we can have 4G devices. What is G? What is G? Yeah.
This is gigabytes, right?
Giga. Does it say bytes? So this number of devices.
Or giga devices.
Right? So we have, is it that or 64 MB? No, I think this is the size. This is the size of those devices. So we are essentially almost the same number of chips per wafer, bigger wafer, but we can have many more devices now in that wafer. Right? So we can push to have bigger wafers, but it requires the whole equipment setups to change to that bigger wafer size. And that means lots of huge investment. So apart from the basic processing or processes, we have to know how industry is dictating what is being used. So it has done major transition to 450 millimeter wafers, which are how much is that? 16 inch. It's called 16 inch wafer. So, but I think it's 18 inch. It should be 18 inch. 450. And I
It's
think
25 centimeter, right?
now 100 is 4 inch. So 400 is 16 inch. So it's 18 inch wafer. Yeah. So these are huge wafers, and this has happened in every generation. Whenever there's been a size change, the whole equipment has to be changed.
Does that mean we get cheaper equipment for our clean room eventually for industry?
Now, the clean rooms or research labs are historically, as far as I know, are stuck on 4 inch wafers or smaller. 4 inch wafers, because what we do is we make proof of concept devices. We're not producing, we're not in production of those. So we are essentially doing a lot more with 4 inch wafers. Think about it, even a chuck which we use to hold a wafer, you cannot use a 2 inch wafer chuck with a 4 inch wafer, because that will have too much vibration to it once you rotate it at 4,000 RPM, for example.
Does that actually create process difficulties? Like, does your spin coating still work with the same chemicals when you got that much area?
Okay, so that's now the chemical side, right? So you apply some, I'm talking about simple mechanics of this, that the equipment has to be completely changed when you do this shift from one side to the next. So essentially what we do is we use different chucks, 2 inch to 4 inch wafer, but that's simply using 2 chucks over whatever size of your wafer is. But when you talk about industry, then so the whole equipment needs to be changed, because then you don't alternate between those different sizes. Right, so now we looked at this list before. So let me touch upon some of these things, and then we'll treat each one in their own lecture. So photolithography, bringing this, I think we did this last class. So essentially you start with the wafer, but you want this whole complex structure on that, which will be a transistor, right? So a number of steps of lithography will be needed. What is lithography again? We use these transparent media, which can be a glass plate, to define regions of opaque parts and transparent parts, and we shine light through it. That results into a shadow on a wafer, which is coated with a photo sensitive material that translates that image onto the surface of that wafer, and we do whatever process comes after that. So this is again, we have looked at this guy again. So what does lithography do? A VLSI designer or a group of designer makes the circuit layout. They might have multi-layers of circuit, which means that as many number of masks need to be made. Masks are made by maybe E-beam lithography. So whatever process we use, essentially that results into a transparent substrate which has some parts which are made opaque, right? And those parts are essentially, they define the regions of the devices that need to be made. We use this guy into what we call a lithography system. So this is my mask, and I shine the light. Light travels through some optics, results into formation of this design into that photoresist material. Essentially, it doesn't make that design. What it does is it changes the property of that photoresist material on those places wherever that light reaches. Right? Use photolithography use ultraviolet, 365 nanometer, 405 nanometer. So there are different wavelengths that we use. So at that wavelength, that photoresist material which is coated on that wafer undergoes chemical changes. Just like what was that? Photographic paper, right? In dark room, when we have red light, so that photographic paper doesn't get, doesn't undergo chemical changes in wavelength of red light, but it undergoes the wavelength of the light that they use to shine the negative, right? Results into exactly same way. So light shines, it results into changes on that photoresist material, certain places. After shining the light, we dip the wafer into solution called developer, and results into that pattern. So photoresist is spread over the whole wafer. So let me show you essentially what happens. So I have a silicon wafer, I've oxidized it, right? So it has oxide. What do? I coat it with photoresist material. I'm calling it positive photoresist. We'll see what does positive mean later on. Essentially, positive means wherever the light shines, that area will be removed later on. Right? So I coat it with positive photoresist. Coating is, we use that chuck to hold on wafer. We rotate it at 4,000 RPM and we apply a liquid in the center of the wafer. First we put the liquid in the center of the wafer and then we spin it. Think about it. What will happen to the liquid? It will fly off. While it flies off, it's going to result into a thin uniform layer of the surface. We make a big puddle of that resist on that. We essentially cover the whole wafer with that puddle of resist material. It's liquid. So once I spin it at 4,000 RPM for 40 seconds, the thing just flies off. And it leaves behind a very thin layer of resist. If I suppose I have two chucks, I spin for 4,000 RPM, the other one I spin for 6,000 RPM. Which one is going to give me a thinner layer of resist?
6,000.
6,000? Do you agree? Right? Of course. Now, if I have two, one is both are rotating at 4,000, I spin one for 30 seconds, the other one for 50 seconds. Which one is going to give me thinner resist layer? 50 seconds. You all agree? If I use exact same rotation at the same time, I use a more viscous resist and a less viscous resist. Which one is going to give me a thinner layer? Less viscous. So we know all this by common sense. These are all the parameters that go into that process. We want specific thickness of resist because it will depend on what is the dose of the light that I shine, and that will thickness will define how deep that can be. We'll look at that. But these are all common sense things. So what we do is we apply this resist by that process where we apply certain photoresist for, and we spin it for a certain time at certain RPM. Results into certain thickness of resist. And now I take that from that chuck and I put it into a machine what I call a liner. A liner essentially has a slot where I put the mask. It has a light source at certain wavelength, and that wavelength is something that this resist is very sensitive to, right? So what I do is I may or may not remove silicon oxide from this, but I use a mask which has certain regions which are opaque for UV, certain regions which are transparent for UV. UV shines through. Wherever it shines through, the resist undergoes chemical changes, right? So resist has chemically changed. So I shine it. I should remove my mask first, and of course I shut off my UV. So this is Microsoft was taking the order. So I shine it. I take it out. So I have photoresist all over. It's not gone yet. Now once I'll put it into my developer solution, it's gonna wash away that part which was gone at chemical changes, right? So that gives me a wafer with pattern defined in photoresist. But photoresist is a polymer. I'm gonna remove this. I'm gonna transfer this design now into hard material, which is silicon dioxide. So I do etching and I remove silicon dioxide. Now I can just wash photoresist. What do we What's a very common material we use to remove dried off chemicals? So we have chemicals that dry off. What do we? Acids.
Water.
Acetone, right? Nail polish board. Dried off chemicals. Right? So acetone, chemicals like acetone is some can remove photoresist. And I don't need resist because I've transferred that pattern into hard material, which is silicon dioxide. When I'm saying hard, photoresist is just a polymer. If you put a scratch with your, even if you touch with your finger, you'll see it's gonna have grooves of your finger. Right? So it's but anyway, so this is what we do. Then we remove our resist, and now we have our pattern transferred. So this was, I'm just showing you. The actual thing will be a two-dimensional surface with all the openings for sources and drains and whatever. So essentially, this is what we do. So PR changes chemically. It's time. Question.